Hello, I'm Jae-Yun from Software Analysis Lab in the last semester of Master course, and I present about my paper, the FeatMaker Automate Feature Engineering for Search Strategy of Symbolic Execution. This paper is published in FSC in one of the top software engineering conference, and it is presented at Brazil in this July. Before starting, I'll briefly introduce our lab. We are advised by Professor Soo-Young Cha and studying about software engineering, including software testing. Specifically, we research about automated testing methods such as symbolic execution and fuzzing. We aim to submit and publish papers to top-tier software engineering conferences like ICSE and FSE, and you can check our publications in the page of our lab. And we are looking for students to work with, and if you have any interest, please mail to our professor or me. And I think if you want to concentrate on your own research, then our lab can be a good option. Then let's start the presentation. I think most students are not familiar to symbolic execution, so I provided brief explanation about it. Symbolic execution is a software test method that executes the program symbolically. It manages each path of the target program as a set of symbolic branch conditions, and each path is called state. It iteratively forces the state based on conditional statements and selects the state to execute. Well, it's quite difficult to understand, so let's see how it works with simple example. At first, it replaces the input of program with symbolic value alpha and beta. So input x and input y would be replaced with symbolic variable and start with the initial state, state 0, which have the empty symbolic branch condition set. Then symbolic execution execute the initial state and it meets the first conditional statement, which is highlighted with green color. And in this example, both cases, true and false, are satisfiable for the condition. So the state forks and each state will be updated with corresponding symbolic conditions. Next, we have to select one state to execute in next iteration. In this example, state 1 already reached the end of the program. So state 0 will be selected and executed. When we execute state 0, it meets second conditional statement, which highlighted with yellow color. And as the first condition was, the second condition can satisfy in both cases, true and false. So state 0 fork again, and its state will be updated with the branch conditions again. Symbolic execution repeats these sequences until time budget expires or there are no more states to execute anymore. And in this example, total 3 states can be generated and symbolic execution moves to next step. In this step, symbolic execution generates test cases satisfying all branch conditions in each state using SMT solver. For example, state 0 can be converted to x equals 0 and y equal 2. The SMT solver is the technique to find answer satisfying the given formula, and it is the separated topic, so we didn't include any explanation about it. I'm sorry for that. And finally, those generated test cases are evaluated with two criteria, whether they can find new bugs or they can cover more code areas than other test cases. And we can say the final goal of symbolic execution is generating better test cases in a limited time budget. Then someone can say, how about executing all the states in the program? However, it is not that simple problem because of the state explosion. The number of states increase exponentially with the number of conditional statements. For example, grep have more than 80,000 states in its code, and there would be very many states generated by grep. So executing all of them is impractical for real-world program due to limited costs. So state explosion is open challenge for many domains, and to mitigate this, identifying promising states became one of the most important issues of symbolic execution, and many prior works suggested their own method to achieve that goal. And those methods are called search strategies. Then let's see a simple real-world example. When we want to buy the cheapest item, we will follow two steps. We first check price of all items and select the cheapest price. This simple example shows us two main components of search strategy. The price works as a feature to represent all items in the same format, and selecting a cheapest price works as a method to prioritize those represented items. These basic designs are applied on strategies for symbol execution as well. State feature represents states, and scoring function prioritizes those represented states. By defining two components, we can design various search strategies. Then let's see existing strategies. In most early strategies, they used a single feature for their design. For example, depth strategy uses the number of conditions exercised by each state, which is called depth, as a single feature and selects the state with a larger value of depth. They used quite simple design, and because of that simple design, the single feature strategies have clear limitations. They always used fixed feature and a fixed scoring function regardless of the target program, and they result in varying performance depending on the target program. The plots on the slide contains code coverage results of various strategies and show top 6 of them on two different programs, PTX and Combine. On PTX, red strategy achieved best performance, but it ranked 4th on Combine. And in opposite, the blue one, the first strategy on Combine, is out of top 6 on PTX. This shows very unstable results. So to mitigate this problem, recent strategies using multiple features have been proposed. Lurch is one of the such example, and it's introduced in 2021. And it represents its state as a multi-dimensional vector using 10 features and scores its state with a trained AI model. However, these multi-feature strategies still have limitations. All those features they use must be manually designed. For Lurch, authors had to manually design 10 features, and Paradise, which is another multi-feature strategy, used 26 manually designed features. And also, even with hard work to design, their quality is not guaranteed. For example, two features from Paradise were useless for some programs. Two plots on the slide show the value of one feature for every state, and as we can see, the most of them, over 96%, have the same value, and we can conclude that this feature is not that helpful to identify promising states. Moreover, those manually crafted features must be redesigned for each symbolic execution tool to use. For example, Paradise implemented two symbolic execution tools, CLE and CREST, and the features for each tool were not compatible with each other. So they have to redesign new features for CLE after they designing 40 features for CREST. So we try to solve all these issues by automatically generating state features from scratch. More specifically, we intended to use only general information which is applicable to all symbol execution tools without relying on any prior knowledges. To achieve the goal, we used branch conditions as state features. As mentioned in the explanation of symbol execution, branch conditions are the most critical data to determine the input of test cases. And additionally, they are the most common information managed by almost all symbolic execution tools. And in detail, we used each branch condition as a Boolean feature. For example, let's assume that there are four features, green, blue, red, and orange conditions in total three states. Then state 0 has the green and red conditions, so state 0 can be converted to the four-dimension vector 1, 0, 1, 0. And other states can be converted in same format in same way. So now we defined how to represent states, so we must define the corresponding scoring function. We use the weight vector including weight for each feature as a scoring function. By multiplying weight vector and converted states, we can get scores of state easily. And each weight value for each feature will be updated during the testing budget with a data-driven approach. And how we update them will be introduced in later part of presentation. So now we have defined two main components of the search strategy, but there remains the challenge that there are too many branch conditions. The graph on the slide shows the number of the total unique branch conditions generated during 24-hour symbol executions of 4 different benchmarks. And in the case of make, the total 60,000 branch conditions are generated, and collecting all of them as state features results in an impractically large weight vector. So we should retain only the necessary branch conditions. So including the key ideas I explained and methods to address the mentioned challenge, we propose a novel technique named FeatMaker. FeatMaker collects data by performing multiple short symbol execution and iteratively updates the state features and scoring function till time budget expires. Then first, let's check about how FeatMaker generates state features. FeatMaker collects branch conditions from filtered data to maintain a reasonable number of state features. The data contains branch conditions and coverage of each test case. And coverage means the set of covered branches, and it can be achieved by executing each test cases. So to filter this data, we clustered it and removed unnecessary clusters. In detail, at first, FeatMaker clusters branch conditions based on their coverage. Let's assume that the total data has been classified to 3 clusters based on 3 unique coverage C0, C1, C2. Then FeatMaker retains the minimum number of clusters that is necessary to cover all the covered branches. We utilize setCover problem in this step. In the example of slide, there are 5 branches in total, and we can cover all of them with 2 clusters, C0 and C2. So FeatMaker considers C1 as unnecessary clusters and remove it from cluster set. And as many students knows, the set cover problem is NP-complete problem, so it is hard to find the exact answer, so we use greedy approach for this step. And then by collecting all branch conditions from remaining clusters, FeatMaker finally generates new state features for next iteration. And next, let's see how FeatMaker makes corresponding scoring function for new state features. On top level, FeatMaker generates new scoring function, which is similar to well-performed ones. For that, FeatMaker had to identify good weights and sample new weights from distribution of them. Then how can we identify well-performed values? For that, FeatMaker grades all used weights of each feature based on the coverage result. In the result, with a value covered more and new branches, then that value gets higher grade than other values. After grading all used values, they would be classified to 3 groups, and FeatMaker finds good weights and bad weights. For this step, we used most basic clustering method, k-means clustering, with 3 for k value. And then we check statistic similarity of two groups. If good weights are not similar with bad weights, then FeatMaker sample new weights from distribution of good weights. In opposite case, if two groups are statistically similar, then FeatMaker samples new weight from uniform distribution for that features. And for the case of not used features, FeatMaker uses uniform distribution too. And by repeating all these steps for all state features, FeatMaker can make new scoring function. And through these steps I've explained, FeatMaker updates state features and scoring function and repeat until given time budget expires. This was how our tool FeatMaker works. And then let's move to the experimental evaluation of our tool FeatMaker. FeatMaker is implemented on top of CLI, which is most widely adopted symbolic execution tool. And we took 24-hour experiments on 15 benchmarks and compared with 4 baselines, Paradise and Lurch for multiple featured strategies, and SGS and Depth for single featured strategies. And those 15 benchmarks were collected from baseline works. And we filtered some too small benchmarks or some benchmarks that is not suitable for symbolic execution. First result to report is the aspect of code coverage. For code coverage, FeatMaker showed significant improvements when compared to baseline strategies. FeatMaker achieved best performance on all 15 benchmarks, and especially it covers 37% more branches on GOG and 45% more on grep. And for more detail, I provided recruited ranks and total coverage of each baselines. And for total coverage of all 15 benchmarks, FeatMaker covers 30% more than state-of-the-art strategies like Paradise and Lurch. And we observed some interesting results from the recorded rank. For general strategies with multiple features, like Paradise and Lurch achieved better results than single-featured strategies. But those strategies still achieved unstable results depending on the target program, unlike FeatMaker. At least in this experiment, we can say that FeatMaker is the only search strategy that truly achieved stable, good result. We collected only crash-occurring bugs which are reproducible on original benchmarks, and FeatMaker detected 15 bugs in 6 benchmarks, and 6 of them were not detected by other strategies. And in the case of exclusively detected bug of find, one of them was not fixed in latest version, which was available before the paper submission. So we reported it and it was confirmed. So you can check it on the webpage of Find Details. The last part of experiments is about the number of state features. One of our goal was reducing unnecessary branch conditions from the total set, and we find that our tool successfully removed 83% of branch conditions on average on 15 benchmarks. And our tool used in experiments is available with Docker container image and GitHub. So if you have any interest, please visit following links on the slide. And for conclusion, existing state features for search strategy have obvious limitations. Their performance varies depending on the target program, and all state features had to be manually designed based on the human insights. So to mitigate those limits, we suggested FeatMaker, a technique that automatically generates state features using branch conditions. And our technique was experimentally verified with significant improvements on both aspects, coverage and bug finding. This is the end of my presentation, and thank you for your listening. If you have any questions, please send the email to my email on the slide. Thank you.